You've heard it 1,000 times. We're going to Mars, like it's just the next stop after the moon. But the truth is way harsher than the headlines. Right now, humanity is basically pinned to a tiny bubble around Earth and the moon, trapped by gravity, radiation, fragile life support, and brutal physics that does not care about our dreams. In this video, we're going to walk through step by step why going beyond the moon with humans is not just hard, it's almost impossible with the technology, budgets, and risk tolerance we actually have. By the end, you'll see why every plan that sounds simple on paper turns into an exponential nightmare the moment you try to scale it past lunar distance, and what would have to radically change before a human footprint on Mars or beyond is anything more than a nice poster on a wall. But before we continue, please subscribe to the channel to give your support. Let's continue. From the launch pad to low Earth orbit, a crewed rocket needs about 9.4 kilometers per second of total speed change. That's roughly 34,000 kilometers per hour, around 21,000 miles per hour. This isn't one smooth push, it's a series of burns and staging events, all of which have to work. Almost all of the rocket at liftoff is just propellant, not habitat, not cargo, not shielding. By the time you're in orbit, a few hundred kilometers up, the beautiful giant rocket from the launch video is gone, thrown away or burned. What's left is a small spacecraft already short on mass and energy budget, and you haven't even gone anywhere interesting yet. Now look at the next step. The moon is about 384,400 kilometers away, around 238,855 miles. In space terms, that's close. It's about 10 laps around Earth's equator. But distance alone is not the real problem. The problem is how much extra speed you have to add to your spacecraft to reach that distance on the right trajectory. From low Earth orbit, you still need roughly 3.2 kilometers per second of additional speed to enter a path that intersects the moon's orbit, what we call a translunar injection. That burn has to be precise. The timing and direction need to be just right, because you're not steering on a road, you're following along a curved path through a moving gravitational field. If you underperform that burn, you don't almost reach the moon, you miss it completely or get stuck in a bad orbit with no fuel to fix it. So already you've spent 9.4 to reach orbit and another 3.2 to go to the moon. You've paid a huge energy bill just to reach the nearest major target in space. Here's where going beyond the moon gets ugly. From low Earth orbit to a Mars transfer, you now need about 4.3 kilometers per second instead of 3.2. On paper, that sounds like, okay, just one more kilometer per second, not a big jump. But rockets don't care about your intuition. They care about an exponential relationship between speed and propellant. That extra 1 kilometer per second can mean dramatically more fuel, bigger tanks, stronger structures, and suddenly your nice moon-capable vehicle is nowhere near enough. This is the core of the rocket equation problem. To get more speed, you add more propellant. More propellant means a heavier vehicle. A heavier vehicle needs even more propellant to reach the same final speed. It's a loop. At the kind of speeds we're talking about, adding just 1 more kilometer per second can almost double the amount of propellant you need. And remember, you're not just pushing fuel, you're pushing everything else too. Crew systems, life support, water, oxygen, radiation shielding, spare parts. Every kilogram you add for safety and comfort now explodes the fuel requirement, which then explodes the launch cost. So when you look at beyond the moon missions, you don't just scale up an Apollo-style stack. Apollo worked because it accepted short mission times, thin margins, limited shielding, and very high risk by today's standards. The Saturn V weighed about 2,800 metric tons at launch, and it sent on the order of 45 tons toward the moon. That's roughly 1.6% of the initial mass actually going on the deep space leg. That ratio already tells you how brutal the physics is. Almost all of the system is sacrificed just to throw a small capsule and lander to lunar distance and bring them back in under 2 weeks. Now try to imagine the numbers without getting poetic. A Mars-class mission needs a much larger habitat, much more life support, much more shielding, and enough supplies for years, not days. You're talking about tens of tons of extra hardware, maybe hundreds, plus the propellant to push that hardware. With chemical rockets capped at around 4.4 kilometers per second exhaust velocity, that means stacking launch after launch after launch, assembling a giant interplanetary ship in orbit, and still living right on the edge of what's possible. Current heavy-lift rockets struggle just to send a few tens of tons to the moon. Scaling that to a fully shielded, fully redundant, multi-year deep space ship quickly becomes unrealistic. That's why, in practice, the moon looks like the outer edge of what our current propulsion and mission architecture can handle. You can still use large chemical rockets, brutal but short missions, and relatively modest shielding. You can still return in a few days if something goes wrong. The energy and mass requirements are just barely within what we can build and pay for. Push that same approach to Mars or beyond, and everything breaks. The fuel required is too high, the vehicle is too heavy, the launch count is too large, and the cost and risk shoot past what any agency or company will accept. So the first hard truth is this: Earth's gravity and the physics of rockets together create a kind of practical boundary. Technically, the laws of physics don't forbid you from going beyond the moon, but the amount of mass and money you need with chemical propulsion makes it almost unreachable for humans right now. The moon sits right at that edge, close enough that we can just about brute force it with huge rockets, but far enough that everything beyond starts to look impossible with the same tools. And here's the next problem. Even if you somehow pay that insane energy bill, even if you build the massive vehicle and escape Earth's gravity for good, you then leave behind something else that has been quietly protecting you your whole life: Earth's magnetic field and atmosphere. Once you go past the moon for months or years, it's not gravity that's trying to stop you anymore. It's radiation, constantly hitting your body and your electronics, with no real off switch. On the ground, you live under a good shield. Earth's magnetic field and thick atmosphere deflect and absorb most of the high-energy particles coming from the sun and from deep space. Your typical radiation dose at the surface is around 2 to 3 millisieverts per year, depending on where you live. That number, millisieverts, is just a way of counting how much biological damage the radiation can do, not just how much energy it carries. It's low enough that for most people, it never becomes a big personal issue. Now compare that to a crew on the International Space Station. The ISS flies in low Earth orbit, about 400 kilometers up, still within Earth's magnetic bubble, but with much less atmosphere above it. Up there, astronauts can pick up around 50 to 100 millisieverts in a 6-month stay. So in half a year, they get something like 20 times a typical yearly ground dose. That is already a big jump, but it's still in a range that space agencies are willing to accept because the missions are limited in length, the crew is monitored constantly, and crucially, they are still close to Earth and inside most of the magnetic protection. Now look at the Apollo missions. Those crews had to go through the Van Allen belts, regions of charged particles around Earth, then cross open deep space to the moon and back. That sounds like a radiation nightmare, but they survived it with relatively low doses, around 5 millisieverts per mission, roughly like a few medical CT scans spread over a week. How did they get away with that? Simple. Time. The total mission lasted about 10 to 12 days, end to end. They passed through the belt quickly, on carefully chosen paths, and they didn't stay in deep space for long. For radiation, dose is the product of intensity and time. If the intensity is high, you just make sure the time is very short. Now switch to the kind of mission everyone talks about, a round trip to Mars. You're no longer talking days, you're talking hundreds of days each way, plus time in orbit or on the surface. Even with optimistic assumptions, at a quiet part of the solar cycle, a Mars mission could hit each astronaut around 870 to 1200 millisieverts of total deep space dose. That is more than 10 to 20 times Apollo, and it's getting close to or even beyond typical career limits that agencies like NASA set for astronauts, roughly 600 millisieverts over a career for many age categories. Once you go past those limits, the extra risk of cancer and other long-term effects starts to look unacceptable by current standards. And that's just from the constant background radiation. It doesn't even count a worst-case solar event in the middle of the flight, a big solar particle storm that could spike the dose over a few hours or days. For ISS crews, if something like that happens, they can hide in a better shielded part of the station, and they still have Earth's magnetosphere helping. In deep space, past the moon, you have no natural backup. If the shielding is not enough, the radiation just comes in. The main problem is not the kind of radiation you see in a hospital X-ray. Out in deep space, a big part of the threat is galactic cosmic rays, particles coming from outside the solar system. These are heavy atomic nuclei, like iron, stripped of their electrons and moving at a significant fraction of the speed of light. They carry huge energy, and they don't care about your spacecraft wall. When they hit the metal or plastic of the hull, they can smash nuclei apart and create showers of secondary particles. So you get the original particle plus a spray of extra radiation inside the cabin. That's why just making the wall thicker is not always a simple fix. Past a certain thickness, you start turning one very energetic particle into many somewhat less energetic particles, which can still damage cells and DNA. Space agencies and researchers talk about shielding in terms of grams per square centimeter. That just means how much mass per unit area the radiation has to pass through. A thin aluminum shell might give you a few grams per square centimeter. To seriously cut cosmic ray doses, you might need several tens of grams per square centimeter, using materials rich in light atoms like hydrogen, for example, water, polyethylene, or special plastics. In simple terms, that's more like a thick wall of material, not just a metal skin. Think in meters and feet, not millimeters. But here's the catch. Mass is the enemy of rockets. Let's say you want to surround a small crew habitat with enough material to bring the dose down to something close to what ISS crews get, even on a years-long trip. You quickly end up with many tons of extra shielding per person, maybe dozens of tons, depending on geometry and materials. Every ton has to be launched out of Earth's gravity well at the cost we talked about earlier, 9.4 kilometers per second toward it, then more to go beyond. The more shielding you add to protect the crew from radiation, the more fuel you need, the bigger the rocket has to be, and the more launches you need just to build the ship. This creates an impossible trade with our current technology. On one side, you have human health limits and strict rules about how much radiation an astronaut is allowed to receive over a mission or a career. On the other side, you have brutal launch mass limits and rocket performance. If you keep the spacecraft light enough that present-day rockets can send it beyond the moon without insane cost, the shielding will probably be too thin, and the crew will take doses that are above today's acceptable limits. If you build the shielding thick enough to really protect them, the spacecraft becomes so heavy that no realistic set of chemical rockets can throw it into deep space at a reasonable cost. You can try clever tricks, like putting water tanks and food stores around the crew quarters to act as extra shielding, or designing a small storm shelter inside the ship with thicker walls for solar events. These ideas help, but they don't erase the basic conflict. You are forced to choose between more protection and more mass, and beyond the moon, over years, the numbers push you into a corner. The physics of radiation and the physics of rockets pull in opposite directions. So even if you somehow solve the gravity and fuel problem enough to leave the Earth-Moon neighborhood, you immediately hit this invisible kill screen, a constant shower of particles that slowly adds up in your body, raising cancer risk, damaging tissues, and threatening your electronics. And here's the next hard question. Suppose you accept the radiation risk, or you somehow manage to carry all that shielding. Can you then keep humans physically alive and functioning for not 10 days like Apollo, but something like 900 days with no resupply, no quick return, and life support that has to work almost perfectly the entire time? Surviving 10 days to the moon is one thing. Surviving 900 days beyond it is a different game, and your body and your gear both know it. On Apollo, life support was basically a high-tech camping kit. Oxygen came from tanks. Carbon dioxide was pulled out of the air using canisters that you used once and threw away. Water was mostly treated as a consumable you just bring along and burn through. That's what people call open loop. You don't recycle much, you just feed the system from the outside and dump the waste. For a mission that lasts 10 to 12 days, that's fine. The total mass stays manageable, the rocket can lift it, and if something starts to go wrong, you're only a few days from home. But what happens when you stretch that same idea to a Mars-class mission, 2 to 3 years end to end, and you try to keep it open loop? Start with something very basic: water. A human needs around 3 to 5 liters of drinking water per day. Then you add water bound up in food, plus some for basic hygiene. To keep the math simple, call it 10 liters per day per person, about 2.6 gallons. Over 900 days, that's 9,000 liters for one person. 9,000 liters is about 9 metric tons, almost 10 tons, for a single crew member just in water. Put 4 people on the ship, and you're dragging around roughly 36 tons of water, the mass of a small truck, but in orbit. And remember, water is heavy. 1 liter weighs 1 kilogram, 2.2 pounds. Every kilogram has to be launched out of Earth's gravity well and then pushed to deep space. And that's only water. You haven't even talked about the air yet. You breathe in oxygen and you breathe out carbon dioxide, and the numbers are not trivial. An average person uses roughly 0.84 kilograms of oxygen per day. Over 900 days, that's around 756 kilograms of oxygen for one person, close to 3/4 of a ton. With a 4-person crew, you're at about 3 tons of oxygen if you tried to bring it all as tanks and never recycle it. You can't just open a window and refill. Everything you need has to be there at launch or generated from what you bring. On the International Space Station, this problem is already visible, and that's in low Earth orbit, only about 400 kilometers up. The ISS uses complex hardware like water recyclers and Sabatier reactors to turn waste products back into useful oxygen and water. They recover moisture from the air, they reclaim water from urine, they react carbon dioxide with hydrogen to get more water and methane. It's very clever chemistry and engineering. And even with all of that, the station still relies heavily on regular cargo ships, bringing up new supplies and spare parts from Earth. If a key pump or reactor fails, you can launch a replacement in a few weeks because you're right above the planet. Now, take that safety net away. Beyond the moon, there's no cargo dragon, no Progress, no resupply tanker in a convenient orbit. Once you're on a deep space trajectory, you're committed. Every carbon dioxide scrubber cartridge, every water recycling membrane, every filter, every valve, every pump has to last for years. You can't just assume you'll swap it out at the next opportunity. That means the reliability standards explode. You're not designing for months with backup from the ground. You're designing for years with zero external help. And we've never flown a fully closed-loop life support system with humans inside for that long in actual space. So you might say, fine, then we just pack more spares, more cartridges, more filters, more tanks, until we're safe. But that pushes you straight back into the mass problem. Every spare is mass. Every backup system is mass. Every extra tank of water or oxygen is mass. The more you try to protect the crew from a single point failure, the more tons you add to the ship, and the more impossible it becomes to launch the thing in the first place. You end up in a loop. You add hardware to make life support safer, which makes the rocket problem harder, which demands more fuel, which may force you to cut mass somewhere else, maybe exactly where you wanted safety. This is why people say a deep space mission needs to be as closed loop as possible. You want to recycle almost everything: water, oxygen, maybe even parts of the food chain. You want your waste streams to become resources over and over for years. That means you're basically trying to shrink a tiny version of Earth's ecosystem into a tube only a few meters wide, maybe a few tens of meters long. You have to stabilize atmosphere, pressure, temperature, humidity, trace gases, water chemistry, and microbial growth, all in a sealed environment that you cannot open or reset. If the balance drifts, you can't just air out the room. The moon is a good place to test these ideas because you can run weeks-long or maybe months-long missions in a hostile environment, but with the option to send help or bring people home fairly quickly. You can see how well your recycling systems hold up how often you need to swap parts, how often sensors fail, and what kind of unexpected contamination or clogging shows up. You can still treat the whole thing as an experiment with a backup plan. In deep space, beyond the moon, that experimental safety disappears. You either trust your closed-loop system for 900 days straight, or you don't launch. So when people say going beyond the moon feels impossible, a big part of that is this. You're not just moving a crew from point A to point B. You're asking a fragile, complex, Earth-tuned biology to live inside a machine that must behave almost perfectly for years, with no way to refresh supplies and no way to fix major design mistakes once you launch. Life support stops being equipment and starts being your only environment, your artificial planet. And even if you somehow manage to make that closed-loop system work with enough water, enough oxygen, enough redundancy, you still have one more hard problem. What happens to the human body that lives in that system in zero-G for months and years at a time, when your own biology starts to break down just because gravity is gone? The moment you leave Earth's gravity for months, your own biology starts working against you, because your body is tuned for life at about 1 Earth gravity, and in zero-G, all those built-in assumptions start to fail. Start with your skeleton. On Earth, every step you take, every time you stand up, your bones are under load. Your body reads that as a signal. We need this structure. In microgravity, that signal almost disappears. Astronauts in zero-G lose roughly 1 to 2% of bone density per month in the weight-bearing bones, even when they follow strict exercise protocols. That might sound like a small number, but ask what happens on a 30-month deep space mission, out and back with surface time in between. If you don't control it well, that's 30 to 60% loss in key areas, like fast-forwarding osteoporosis. You're talking about bones that are thinner, more fragile, more likely to crack under stress. Now, think about what that means in practice. You arrive at Mars or some deep space target with weakened hips, spine, and legs. You try to work in a bulky suit, you trip, you fall. A minor impact that would be nothing on day 1 on Earth could become a fracture on day 900 in space. Back on Earth, you could go to a hospital, get surgery, rest in a proper bed, use crutches. Out there, your hospital is whatever fits in the ship, and your ability to immobilize someone and keep them productive is very limited. So the bone loss isn't just a graph on a medical chart. It's a direct hit to your chances of handling emergencies and doing any serious work when you arrive. Then there's the muscle and the cardiovascular system. On Earth, your muscles constantly fight gravity just to keep you upright. Your heart has to pump blood uphill to your brain. Your whole circulation system is tuned to 1G. In zero-G, your muscles don't carry your weight, and your heart's job gets easier in a way that sounds nice but is actually dangerous. If you don't push back, your muscles start to atrophy. They literally shrink, and your heart and blood vessels decondition. Blood volume can drop, your ability to handle standing up in gravity gets worse, and your reflexes for regulating blood pressure get weaker. So what happens when you come home or step on a planet with even partial gravity, like Mars at about 38% of Earth's gravity, or the Moon at about 1/6 G? Many astronauts returning from 6-month ISS missions feel dizzy, weak, and unsteady when they first stand up back on Earth, and that's after dedicated rehab plans. For them, it's temporary. They're surrounded by doctors and support. Now extend that to a small crew in deep space with no medical team on standby who still need to climb ladders, move equipment, and fix problems under time pressure. If someone can't stand without almost blacking out, they're not going to be very helpful in a crisis. The effects don't stop at bone and muscle. Long-duration ISS missions have revealed something called Space-Flight-Associated Neuroocular Syndrome, or SANS. In simple terms, fluid in your body shifts toward your head in zero-G, because gravity is no longer pulling it down toward your legs. That extra fluid can increase pressure in and around the eyeball, flattening it slightly, changing its shape, and pushing on structures near the optic nerve. Astronauts have reported changes in vision, like needing different glasses during or after flight, and scans show changes that suggest the brain and its surrounding fluid spaces are being affected too. Ask yourself what that means halfway to Jupiter or halfway to Mars when you're months from any possibility of real medical imaging or intervention. If someone's vision degrades significantly, they might not be able to read displays, aim instruments, or handle fine manual work. If the underlying brain changes have long-term consequences, you might not even see the full impact until it's too late in the mission. Right now, we don't fully understand how to prevent SANS. We just know it happens, and we're still collecting data in low Earth orbit, close to home. To slow all of this down, ISS Aarhus spend a huge amount of time exercising. Roughly 2 hours per day are blocked off just for mandatory workouts using treadmills with harnesses, cycling machines, and resistive exercise devices that simulate lifting weights. That's not for fitness or aesthetics, that's just to try to keep losses under control. Even with that, they still come home with measurable bone and muscle loss, and they still need rehab. For a Mars-class mission, those 2 hours per day per person mean a lot of extra food, extra oxygen, extra wear on the life support hardware. Also, the crew can tread water biologically. So you run into another trade. You need heavy exercise to keep the crew functional, but heavy exercise increases the load on your already stressed life support system. More food consumed means more waste processed, more CO2 generated, more oxygen needed, more mechanical wear on the machines, and more risk of failures. If you try to reduce exercise to save supplies, the crew's physical condition deteriorates faster, and your ability to complete the mission safely falls off a cliff. There's no free option. You're always paying, either in consumables and hardware stress or in human health. People often say, okay, then just use artificial gravity, just spin the ship. In theory, if you build a rotating habitat, you can simulate 1G or some fraction of it by using centripetal acceleration, so someone standing on the inner wall feels weight. But look at what that would take. To make the rotation comfortable, you need a fairly large radius. Tens of meters, maybe more, so that the spin rate is slow enough that people don't get motion sick. That means a big, complex structure with strong joints, bearings, and balance control. It adds a lot of mass and a lot of engineering risk. Right now, we have never flown a large, spinning, crude artificial gravity system in space, not even in low Earth orbit. It's still in the concept and ground test phase, not in the operational toolbox. This is where the moon looks different. On the lunar surface, you at least get about 1/6 G. That's not proven to be enough to protect bone and muscle, but it's more than 0 G. You can design work routines and exercise gear around that partial gravity. You can study how human biology responds over months, and if something goes badly wrong, you still have a path, however risky, to get people back to Earth in a matter of days. In deep space, between worlds, you're in 0 G for months at a time, with no natural gravity anywhere, and no quick exit if the human body starts to fail in ways we didn't predict. So now stack it all together. Bones thinning, muscles shrinking, hearts deconditioning, vision changing, and all of it happening while you are completely dependent on machines that must never seriously fail. Even if you handle the radiation and the life support, you are still taking a healthy human, optimized for girth, and slowly pushing them into a state where just standing and walking in a normal gravity field becomes a challenge. And while your body is weakening, the outside environment isn't passive either, because once you head into deep space for years, you're also exposing your ship to brutal temperature swings and constant high-speed dust impacts, things that don't care how well you trained. They just hit over and over. Deep space isn't empty. It's an unregulated battlefield of heat, cold, and high-speed shrapnel, and your spacecraft is stuck in the crossfire for as long as you stay out there. Near Earth orbit, in full sunlight, exposed surfaces can go above plus 120 degrees Celsius, around 250 degrees Fahrenheit. Put that same surface in shadow and it can drop below minus 150 Celsius, about minus 240 Fahrenheit. That is a thermal cliff of almost 300 degrees from one side to the other. Metal, composites, seals, circuit boards, all of it is constantly expanding and contracting as you move in and out of sunlight. On a short mission, maybe 10 days to the moon and back, you can design the structure and electronics to tolerate a limited number of these cycles. You test them, you overbuild a bit, and you trust your data. But what happens when you stretch that to 900 days? Thousands of orbits, thousands of transitions between hot and cold. Every weld, every bolt, every glue layer, every cable is being stressed and relaxed over and over. Tiny cracks can grow, lubricants can dry out or migrate, insulation can fatigue. A wire that would last a decade in a stable lab environment might start to fail if you force it through constant flexing and thermal change. Once you leave low Earth orbit, you can't park at a space station to patch things up. If a radiator line cracks or a seal on a hatch starts leaking vacuum, you don't get a second chance. You might think, fine, just insulate more, use coatings, blankets, and heaters to smooth things out. That's exactly what engineers already do. Multi-layer insulation, active thermal control loops with pumps and radiators, heaters on critical areas. But all of that costs power, volume, and mass. Radiators have to dump heat to space, and when they face the sun, they become heat absorbers instead. You end up with a delicate balancing act, shuffling heat between zones and timing when surfaces face the sun or darkness. On a 10-day lunar run, if a heater degrades a bit early, you can write it out. On a multi-year deep space mission, a slow drift in thermal performance can turn into a runaway problem, freezing lines or overheating electronics. And that's just temperature. What about all the solid particles racing around you at insane speeds that you can't see coming and can't dodge? The space between planets is filled with micrometeoroids, tiny grains of dust and rock, some smaller than a sand grain, some larger. They travel at tens of kilometers per second relative to your ship. Call it 50 kilometers per second, about 112,000 miles per hour, as a typical dangerous speed. At that velocity, even a grain the size of a sand particle carries energy similar to a bullet because kinetic energy grows with the square of velocity. Double the speed and the energy goes up by 4. At these speeds, there is no warning and no soft impact. If one of these grains hits a thin metal wall, it vaporizes itself and part of the wall in a tiny explosion. You don't just have to worry about the main pressure hull. Radiators, solar panels, antennas, sensors, cable runs all stick out into space and can be damaged or cut by a micrometeoroid. A hit that shreds a solar panel string might not kill the crew immediately, but it could slowly starve the ship of power. A hit that takes out a radiator segment could cause overheating in your life support systems or propulsion. Worst case, a particle hits a weak spot in the main hull or near a joint or window, and suddenly you have a rapid depressurization event in a module with nowhere to escape to. So how does mission duration feed into this? Think of it like a probability problem. In a 10-day lunar mission, your ship presents a certain area to the micrometeoroid environment for 10 days. There's a small chance that something important gets hit, but the exposure time is short. In a 900-day deep space mission, you multiply that exposure by 90. You don't know when or where a critical hit might come, you just know that the longer you stay out, the more lottery tickets you are forced to buy in a game where the winning ticket is actually the one you never want to draw. You could say, fine, then just add armor, make the shell thicker. And that's where Whipple shields come in. A Whipple shield is not just one thick wall, it's a multi-layer system. You have a thin outer bumper layer set some distance away from the main pressure wall. When a fast particle hits the outer layer, it shatters and vaporizes before reaching the main structure, spreading its energy over a larger area and giving the inner wall a better chance to survive. For critical areas, you might stack multiple layers, use special materials, and tailor the spacing to the threat spectrum you expect. These shields work. Spacecraft and stations already use them to survive in low Earth orbit where there is both natural debris and man-made junk. But again, every layer you add is more mass, more aluminum, more composite tiles, more standoff structure to hold them. Now apply that to a deep space habitat that is supposed to survive for years, not months, and suddenly you're surrounding the crew cabin, the tanks, the engines, and the critical systems with extra armor. The ship grows heavier, the cross-sectional area grows, and you circle back to the rocket problem, needing more fuel to push more mass, which means bigger launchers, more launches, and higher cost. For short lunar missions, we accept a certain level of thermal stress and impact risk. You design for the 10-day window, add reasonable shielding, accept that the odds of a catastrophic hit in that time are very low, and fly. If something goes wrong but the crew survives, you can often get them back within a few days. The risk window is small, the mission profile is compact, and the level of hardening can stay modest. You're still playing a dangerous game, but you're doing it close to home with short exposure. Once you talk about years in deep space far beyond the moon, the whole risk calculation shifts. There is no quick abort, no nearby safe harbor, no rescue ship. Every extra month you stay out adds more thermal cycles, more radiation dose, more micrometeoroid exposure, more chances for tiny cracks to grow into real leaks, and more opportunities for a single grain of dust at 50 kilometers per second to end the mission. To make that tolerable, you'd need industrial-scale engineering, hulls built more like armored submarines than thin-skinned capsules, thermal systems designed for decades, and redundancy stacked on redundancy. And even if you invest in that level of hardening, you're still stuck on another limit, because the more metal, armor, radiators, and backup systems you bolt on, the harder it becomes to push that ship anywhere at all. Which leads to the next constraint. Even if you somehow build a hardened, long-lived deep space habitat, you still have to control it and support the crew from incredibly far away through a communication link that starts to stretch, delay, and fade as soon as you leave the Earth-Moon neighborhood. Beyond the moon, you're a delayed voice in the dark, and that changes what safe even means, because suddenly the people on the ground can't actually be there with you in real time anymore. Radio waves move fast, about 300,000 kilometers per second, around 186,000 miles per second, basically the speed of light. The moon sits at roughly 384,000 kilometers away, so the one-way time for a signal is about 1.3 seconds. That sounds small, but in a live conversation, you feel it. You speak, you wait a beat, the other person hears you, speaks back, you wait again. It's like a slightly laggy phone call, a little awkward but manageable. For Apollo, that was okay. Mission Control in Houston could still walk the crew through checklists, watch data in real time, and react quickly if something looked wrong. Now stretch that distance to Mars. Depending on where Earth and Mars are in their orbits, the gap can be anywhere from tens of millions of kilometers to over 400 million kilometers. That translates into signal delays from about 4 minutes one way up to around 24 minutes one way in extreme cases. So you ask a question and you don't get an answer for 4 to 24 minutes. Then you respond and they don't hear you for another 4 to 24. A simple back and forth can take almost an hour. At that point, it's not a conversation, it's a slow exchange of audio emails. Think about what that does to troubleshooting. On the ISS, if a valve misbehaves or a pump trips, ground controllers can see it on their screens almost instantly. They can watch the crew's cameras, talk them through a checklist, change software settings on the fly, even restart systems from the ground. In a Mars scenario, by the time Houston even hears we have a problem, that problem has been evolving on the ship for several minutes. By the time advice comes back, the situation might already be completely different, better or worse. Real-time handholding dies because physics has added a delay that no amount of technology can remove. That kills the idea of joystick driving from Earth. For the moon or low orbit, you can still do some remote operations with near real-time feedback. You can steer robotic arms, adjust attitude, send quick commands, and see what happens. But with multi-minute delays, you can't fly a vehicle from Houston the way you might fly a drone. You can only send high-level instructions and hope the onboard systems can handle the details. That means the spacecraft itself has to be more autonomous. Its software has to make more decisions locally, and the crew has to be trained as their own mission control, with deep understanding of systems, failures, and procedures. All of that adds complexity to the design. More autonomy means more code, more sensors, more logic paths, more ways for rare bugs or unexpected interactions to show up. You have to test that software insanely hard because you won't have a flight control room full of experts watching every variable in real time and catching odd patterns early. Instead, the ship itself and the crew have to detect anomalies, classify them, and react, while the ground team acts more like a consultant that reviews data after the fact. Then there's the raw signal strength problem. Radio waves spread out as they travel, like the beam from a flashlight getting wider with distance. The intensity drops with the square of the distance, which basically means if you double the distance, the signal gets 4 times weaker. If you move from the moon's distance, around 384,000 kilometers, to something like 100 million kilometers, typical of a Mars transfer, the ratio is huge. Take 100 million divided by 384,000, then square it, you get a reduction factor on the order of tens of thousands, around 67,000 or so. In plain language, your signal is getting dimmer by roughly 5 orders of magnitude. To cope with that, you use big antennas, narrow beams, sensitive receivers, higher power transmitters, and clever encoding to pack data efficiently. But there's a limit. At lunar distances, you can stream a lot of telemetry, live audio, maybe even decent video. At Mars distances, continuous high-resolution video from a crewed ship becomes expensive in power and bandwidth. You start making choices. Do you send high-rate engineering data, medical data, or live cameras? Something has to give, because you can only push so much information down that link without either increasing power and antenna size to ridiculous levels or slowing the data flow. Less bandwidth means less visibility from the spacecraft from Earth. Ground teams get summaries, snapshots, scheduled dumps, not every single detail all the time. That makes early detection of subtle patterns harder. A weird temperature drift, a small sensor glitch, a tiny pressure change. All could be signs of a bigger issue, but if you don't see them in high resolution and in real time, you might miss the chance to intervene early or to advise the crew before the situation escalates. Put the delay and the bandwidth limits together, and you get a very different safety picture. On Apollo and the ISS, there's a strong sense that mission control has your back. You're never really alone, because dozens or hundreds of specialists are looking at your data second by second. Beyond the moon, the psychological and operational reality flips. You're alone first, with a backup team on Earth that works slowly through a narrow pipe. That pushes agencies to be much more conservative about what kinds of missions they approve, because they know that if something starts to fail, they can't rush in with a real-time fix. This is a big reason hardware risk tolerance shrinks as distance increases. If you know that you can keep a close watch and jump in as soon as something looks odd, you might accept slightly more aggressive designs, new materials, or less mature systems. If you know that any serious failure has to be solved locally by a small crew with limited tools under stress, then suddenly the only acceptable systems are the ones that are incredibly robust, incredibly well tested, and often simpler, heavier, and more conservative. That again feeds back into mass and cost, because ultra-reliable systems usually mean redundancy, over-design, and lots of margins. Now, connect this to everything else you've heard so far. You already have a massive gravity well to escape, a radiation field that wants to hit you constantly, life support that must run for years, a human body that decays in 0G, and the spacecraft being sandblasted by temperature swings and micrometeoroids. Add on top of that the fact that when something finally goes wrong, your best experts are minutes away in signal time, looking at partial data, unable to pull you out in real time. At that point, you can't just say, if it gets bad, we'll abort and come home fast, because the physics of your trajectory starts to lock you in. So the next question is brutal. If your connection to Earth is delayed, limited, and mostly advisory, what does abort even mean when you're already millions of kilometers from home, riding a path you can't easily reverse with no quick way to turn around or to rescue anyone if something goes seriously, irreversibly wrong? On Apollo, a lot of the flight plans were built around something called a free return trajectory. In plain language, that means you launch from Earth, you do one big burn to aim at the moon, and if all your engines suddenly died right after that, the path of your spacecraft would naturally swing you around the moon and drop you back toward Earth using gravity alone. You might not land exactly where you wanted, and the ride would be rough, but the physics itself gives you a chance to come home. That built-in loopback sits at around 384,000 kilometers, and it's not just a nice feature, it's a safety net. That free return option changes the mindset. If something goes seriously wrong on the way to the moon, there is at least a path where you don't need huge extra burns to come back. You still need life support to keep working, you still need power and navigation, but you don't have to completely redesign the mission on the fly. The trajectory itself is doing a big part of the rescue. You are far from Earth, but you are still in a kind of gravitational backyard where you can bend your path with relatively small tweaks and still fall home. Now compare that to what happens when you go interplanetary. To get to Mars or any other planet, you usually use something like a Hohmann transfer orbit. That's a very efficient path, but it's also very rigid. You burn your engines near Earth, you put your spacecraft onto a long, stretched-out ellipse around the Sun, timed so that Mars and your ship intersect at the same point months later. After that initial burn, you're basically on rails. You can do small mid-course corrections to fix your aim, but the main shape of your path is locked in, unless you spend a massive amount of fuel. Here's a problem. Reversing that path or even significantly shortening it is not like hitting the brakes in a car and making a U-turn. To truly turn around halfway to Mars, you would need a speed change on the same order as what you used to leave Earth in the first place, maybe more. That means huge extra propellant reserves, extra engines, extra structure, which your rocket had to lift off the pad on day one. In practice, no one designs a mission that way because the mass penalty is insane. So once you're on that transfer, there's no "let's just go back now" option in any realistic sense. You're committed. Think about what that means for a medical emergency. If someone on the crew has a stroke, a heart attack, a burst appendix, or severe injury halfway to Mars, the universe does not care. You can't turn around and get them to a hospital in a few hours. You are months away no matter what you do. Your ship has to be the hospital. That means diagnostic tools, surgical capability, and people trained not just in basic first aid, but in real, serious medical interventions. All in microgravity, all in a cramped environment. It also means accepting that some conditions we treat routinely on Earth might be fatal out there purely because of time and distance. The same logic applies to hardware. In low Earth orbit or on a lunar mission, if a system starts to fail, you can consider multiple layers of backup, including get home quickly. A pump fails on the ISS, ground teams can help the crew patch it or reroute systems. And if something is truly catastrophic, you can load the crew into a capsule and deorbit within hours. For Apollo, an emergency might mean cutting the mission short and using that free return or a fast return trajectory to bring the crew home in a few days. It's not safe, but it's at least possible. Beyond the moon, that extra escape layer disappears. If a crucial system fails halfway to Mars, your options are limited to whatever you packed on the ship. There is no resupply run, no tugboat, no rapid evacuation. That pushes mission designers into a different regime of redundancy. For a lunar mission, you might accept single fault tolerance, meaning if one unit fails, you have one backup. For a multi-year deep space mission, you start thinking in terms of double or triple redundancy. Not just one backup, but two, plus the spare parts and tools to repair or even improvise replacements. Now scale that across everything that keeps you alive. Power systems, life support loops, pumps, fans, scrubbers, computers, navigation gear, communication hardware, thermal control, attitude control. You don't just need duplicates, you need independent failure paths. You need to separate units physically so one impact or fire doesn't tick them all out. You need spare boards, spare pumps, spare valves, and the diagnostic tools to tell what's wrong when something starts acting weird. This is hardware redundancy squared, and it doesn't come for free. Every layer of redundancy adds mass, volume, and complexity. You need more space inside the ship to store spares, more procedures for the crew to learn, more cables and plumbing to route, more tests to run before launch. And because you're now assuming that repairs in flight are normal, not rare, you also need a workspace, a kind of orbital workshop with tools, clamps, test equipment, and maybe even small manufacturing capability like 3D printers for emergency parts. That turns the spacecraft into a combination of habitat, factory, and repair yard, which again pushes mass and cost up and pushes your propulsion system closer to its limits. All of this is tied to one simple question. How long do you have an abort window? A time period where you can decide, this is too dangerous, we're going home now, and actually act on that decision. In low Earth orbit, abort is always on the table. You can undock, deorbit, and land the same day. On a lunar mission, your abort window is measured in hours or days. You can shorten your stay, fire the engine earlier, and be back in a few days if something forces you to stop. The free return path gives you a baseline backup even if you can't do all the planned burns. Once you push beyond the moon, your abort window in the traditional sense almost disappears. There's no quick burn that magically jumps you back to Earth in a few days. The best you can do is decide between continuous planned and try to limp along and maybe get home months from now with a damaged ship and a stressed crew. That's not really an abort, that's just a slower failure mode. From a safety perspective, that is a huge shift. Agencies are used to missions where, in the worst case, you can at least attempt a rapid return. Deep space missions throw that comfort away. This is why people talk about the moon as the border of our current human safety envelope. It's the last major destination where all the old human spaceflight philosophies still apply. Quick aborts, strong ground support, short exposure times, and trajectories that can be bent back toward Earth without rewriting the laws of rocketry. Beyond that, everything we've relied on for decades, from real-time mission control to real meaningful abort options, starts to crumble. So now stack that new reality on top of everything else. You're stuck on a path you can't reverse, your support is delayed by minutes, your life support has to work for years, your body is getting weaker, and your ship is being hit by radiation, micrometeoroids, and thermal stress. To even try this, you need a spacecraft that is far bigger, tougher, and more redundant than anything we've ever flown. And that brings up the next problem. How do you actually push something like that off Earth and through space when our main tool is still the same kind of chemical rocket we used in the 1960s, already pushed close to its physical limits? You're trying to cross an ocean with technology tuned to hop between nearby islands, and that's exactly the corner chemical rockets trap you in when you talk about going beyond the moon. Right now, your main tool is a chemical rocket engine. The best of these, things like hydrogen-oxygen engines, top out at a performance measure called specific impulse of around 450 seconds in vacuum. You can think of that as a measure of how efficiently the engine turns propellant into push. In velocity terms, that's a velocity of about 4.4 kilometers per second, roughly 2.7 miles per second. That sounds fast, but in deep space terms, it's not fast enough. Because to get big total speed changes, you need to throw away mass at that exhaust speed over and over. And the rocket law that connects all of this is exponential, not friendly. Here's the problem in simple language. Your spacecraft starts heavy, full of fuel. As you burn, you throw fuel out the back at that 4.4 kilometers per second exhaust speed, and the rest of the vehicle speeds up. But the more total speed you want to gain, the higher the ratio between full and empty mass has to be. So if you want a modest speed change, you might get away with a vehicle that's half propellant. If you want the kind of total speed you need to launch from Earth, reach orbit, and then head to the moon or beyond, the math tells you that most of the starting mass needs to be propellant, and only a thin fraction can be structure, engines, and crude hardware. Look at a real example. The Saturn V, the moon rocket, weighed about 2,800 metric tons at liftoff. That's 2.8 million kilograms, or about 6.2 million pounds, a skyscraper-sized machine full of fuel. Out of that, only roughly 45 tons actually ended up going on a trajectory toward the moon, the command module, service module, and lunar module together. That's about 1.6% of the liftoff mass going on the deep space part of the mission. The rest was staging hardware and propellant, burned and dropped along the way, just so that small stack could escape Earth and hit the necessary speeds. That ratio should bother you, because it shows how brutal the physics already is just to reach and touch the moon. Now scale up what you want to do. For Mars or beyond, you're not sending a small, thin-skinned capsule for 10 days. You're talking about a heavily shielded, redundantly supported habitat with thick walls, radiation protection, big life support loops, spare parts, exercise equipment, medical gear, and enough supplies to last on the order of 900 days. That's not 45 tons. That's easily into the many tens, maybe hundreds of tons if you want a realistic safety margin. To push something that heavy using only chemical engines, you either accept tiny speed changes and very long transfer times, or you go back to the rocket equation and see what it demands. And what it demands is ugly. You need more propellant, which means a bigger tank and stronger structure, which means even more propellant to push the extra mass, and the loop repeats. You quickly end up with launch stacks bigger than Saturn V, not just once, but many times, because you're not launching the whole ship in one go. You'd be assembling a massive interplanetary vehicle in orbit piece by piece, each piece needing its own giant rocket to get there. Think about the logistics of that. Multiple heavy lift launches, each in the 1,000-ton class on the pad, each carrying maybe tens of tons of hardware to orbit. You dock segments, trusses, tanks, habitat modules, shield sections, propulsion units. You have to fuel them, check them, integrate power and data, test everything in microgravity, all while paying for launch after launch. And all of this just to create something that has enough total propellant and engine power to crawl out of Earth's well and then still have meaningful thrust left for course changes, braking at the destination, and the trip home. People sometimes say, okay, so stop using chemical rockets. Just use electric propulsion. That solves it, right? Electric thrusters like ion engines or Hall effect thrusters really are much more efficient. Their exhaust speeds are tens of kilometers per second, an order of magnitude better than chemical. In plain terms, that means their exhaust speeds are tens of kilometers per second, so each kilogram of propellant buys you much more speed change. That's why deep space probes use them. They sip propellant and slowly build up huge total velocity over months and years. But here's the catch. Electric propulsion gives you very small thrust. It's like comparing a fire extinguisher to a pressure washer. Chemical engines dump energy fast, huge thrust for a short time, good for launch and big burns. Ion engines deliver tiny but steady pushes, like gently tapping the spacecraft over and over. For a cargo probe, that's fine. You don't care if the trip takes a bit longer, and you don't need to do emergency maneuvers. For a human mission, tiny thrust is a problem. You want the ability to accelerate reasonably fast for trajectory changes, to brake into orbit, and to perform abort maneuvers if something unexpected happens. Electric propulsion alone at current power levels doesn't give you that kind of control. So you end up with a split. Chemical propulsion is strong but wasteful and limited in efficiency. Electric propulsion is efficient but weak and slow. Neither on its own looks like the perfect answer for a heavy, crewed, deep spaceship that has to move large masses quickly enough to keep mission times under control and still offer meaningful safety options. That's why people talk so much about nuclear options. Nuclear thermal rockets, for example, use a reactor to heat hydrogen, then push it out a nozzle. That could, in theory, give you exhaust speeds roughly twice what chemical hydrogen-oxygen engines can do, maybe around 8 to 9 kilometers per second instead of 4.4. Doubling the exhaust speed reshapes the rocket equation in your favor. It lets you get the same total speed with a smaller propellant fraction, or more speed with the same propellant. Nuclear electric concepts go even further, using reactors to power very high-performance electric thrusters, mixing the high efficiency of electric propulsion with a high-energy source that doesn't rely on solar panels. On paper, these ideas start to close the gap. Suddenly, you can talk about pushing a heavy, shielded habitat with less propellant, shorter travel times, and more flexibility in your trajectories. You can think about building in real margin for redundancy and safety without immediately hitting impossible mass numbers. But there's a blunt reality here. Right now, as you watch this, none of these advanced nuclear or high-power electric systems are flying humans in space. They are at the level of ground tests, small-scale demos, or mission concept studies. Funding, technical, and safety hurdles are still blocking the way. So, until something like nuclear, thermal, or advanced electric propulsion actually becomes operational, human missions are tied to the same basic chemistry we had during Apollo. Sure, we've improved materials, engines, and guidance, and we have reusable boosters and better launch economics. But the core physical limit, that 4 point something kilometers per second exhaust velocity, is still there. With that limit, and with all the mass you need for shielding, redundancy, life support, and structure, chemical rockets can realistically keep you pinned near the moon. You can brute force your way to lunar orbit and the surface, maybe build a small base, but stretching that same system to Mars or beyond pushes you into a regime where the mass, the launch count, and the risk all explode. And even if you somehow brute force that anyway, even if you accept a barely workable propulsion system and build a marginal deep spaceship, you still hit one more wall: money. Launching thousands of tons, developing new tech, building giant habitats, and operating them for years is not just a physics problem, it's a budget problem. And the price tag of doing all of this safely is so high that it quietly tells you where the line really is. If the moon is already financially insane, deep space human missions are something past that, and the numbers show it very quickly once you stop looking at concept art and start looking at price per kilogram. In rocketry, cost per kilogram to low Earth orbit is the master number. For a long time, that number sat around $10,000 or more per kilogram to orbit, sometimes much more, depending on the rocket and the mission. Newer systems are pushing that down, sometimes by big factors. But the basic logic doesn't change. Every kilogram you want to move off Earth costs real money. And when you start talking about hundreds of tons, the bill jumps into billions fast. A serious Mars-class habitat with shielding, life support, structure, propulsion, and margin easily ends up in the hundreds of tons range. Even if you optimistically say launch costs drop to a few $1,000s per kilogram, you're still staring at multi-billion-dollar launch bills just to put the mass in orbit before you build the ship, test it, or fly it. So ask yourself, if just lifting the hardware for one deep spaceship costs billions, what does the full program cost when you add design, development, testing, operations, ground infrastructure, and all the support staff? You're no longer in the range of a big science mission. You're in the range of a national-level infrastructure project, like building a major high-speed rail network or a fleet of new power plants, but in space and with much less room for error. We already have one historical warning about this: Apollo. In the 1960s, the Apollo program cost on the order of 25 billion US dollars of that era. Adjusted to today's money, you're talking somewhere in the $150 to $200 billion range, depending on how you calculate it. What did that buy? It bought a rocket family, ground systems, training, and in the end, 6 successful moon landings, plus a few test flights and hardware sets that never flew or only partially flew. That's what it took to send small crews on short visits to the nearest world, with relatively simple habitats and thin shielding. So if it costs that much to do a handful of short moon landings, what does it cost to design, build, and operate a system that can send people to Mars and bring them back over several years, with far heavier ships, far more complex life support, and much tougher reliability requirements? You're not just scaling Apollo by a factor of 2 or 3, you're multiplying complexity across every system, and you're doing it in an era where public tolerance for risk is lower, and regulatory and safety demands are higher. Now look at the value side. The moon at least has a clear package of returns, even if they are not all financial. You get science, you get national prestige, you get a permanent training ground near Earth, and you might get future resource extraction, like mining water ice for fuel, and life support, or metals for industry. Those are potential long-term payoffs that can be tied to ongoing activity, not just one big stunt. Lunar bases can be scaled up slowly, hardware can be reused, and you can spread the cost over many missions. A one-off human Mars mission, or something even more extreme, like a crewed trip to an outer planet moon, doesn't look like that, at least not yet. Right now, a human Mars flight is basically pure cost. Yes, it would deliver incredible science and massive prestige, but there's no clear short-term economic return. No one is shipping back cargo from Mars and selling it. There's no proven market. So any government or company that funds such a mission is committing to spend tens or hundreds of billions of dollars for something that, in practical terms, is exploration and demonstration, not a profit-making project. That's before you factor in insurance and risk. As missions get longer and farther, the chance of losing a crew goes up. There are more days for something to go wrong, more systems that can fail, more exposure to radiation and micrometeoroids, more chances for medical emergencies. Agencies and insurers all know this, even if they don't say it in dramatic language. They implicitly ask a quiet question. At what point does making it safe enough cost so much that it becomes economically impossible to approve? Because remember, making it safer always costs more. If you want extra shielding, you add tons of material. If you want more redundancy, you add entire extra systems. If you want better life support, you invest in long, expensive R&D programs. If you want lower crew risk, you demand more testing, more unmanned demos, more rehearsals, more simulations. All of that adds years and billions. At some point, the curve of risk versus money gets so steep that to shave off a little extra risk, you need to spend a huge amount of extra cash. And that's where decision makers start to quietly back away. This is one reason the moon keeps popping up as the practical goal. Even with its high costs, you can at least argue that a lunar program builds reusable infrastructure, like landers, habitats, and refueling depots that can support many missions. You can reframe it as building a permanent capability, not just a single-shot event. Budgets can be spread across years, and benefits can be tied to many flights, many experiments, many partners. You can do international cooperation, commercial partnerships, and step-by-step expansion. Now, imagine making the same pitch for a multi-year deep space mission. You have to say, we want to spend national-scale money for a decade or more to send a small number of people on a single, highly dangerous trip with no guarantee of direct economic return, and a very real chance that, if anything goes wrong, the entire world watches a slow-motion disaster unfold on live feeds. That's a hard sell. Not because the physics forbids it, but because the financial systems that sign checks have limits. Even with aggressive cost reductions in launch and spacecraft manufacturing, going well beyond the moon with humans still means committing to huge, stable budgets for many years. It means locking in support across multiple election cycles, with leaders who may not agree on anything else. It means accepting that other projects on Earth and in space will get less funding because this deep space effort is draining resources. So far, no country, no coalition, no company has fully stepped up to that level for a true beyond-the-moon human mission. Everyone runs the numbers, looks at the risk, looks at the return, and quietly draws the line near the lunar frontier. So you end up with a strange situation. On paper, we can sketch vehicles that go to Mars. On paper, we can design life support, shielding, propulsion, and habitats. Physics doesn't slam the door completely shut. But when you layer in the real cost of doing it safely and repeatably, the effective wall appears right around the moon. That becomes not just a technical limit, but a financial ceiling. And even if you somehow push through that ceiling, even if you find the money and accept the risk, there's one more barrier waiting, one that isn't just about your crew or your budget. Once you go beyond this dead and mostly sterile moon, you start touching worlds that might have their own chemistry, maybe even their own biology. And then the question changes from, can we survive there, to, do we have the right to touch it at all? And what if we bring something back that we don't understand? Beyond the moon, the stakes aren't just your crew. You're also messing with alien environments, and that changes the rules for what missions are even allowed to fly. Start with a simple case, the moon. The moon has no real atmosphere, basically no air, almost no volatile materials at the surface except a bit of trapped ice and deep, cold craters, and no known biosphere. No rain, no winds, no oceans, no forests. As far as we can tell right now, it's geologically quiet and biologically dead. That makes it the cleanest place in the solar system to learn how to walk in deep space. If you leak a bit of air, drop some microbes from your suit, or leave hardware behind, you're not wiping out an ecosystem. You're not invading a living world. From a planetary protection point of view, the moon is as low risk as it gets. That's why you can be relatively relaxed about contamination there. Suits don't have to be sterilized to hospital levels before every EVA. Landers don't have to be baked and scrubbed the way robotic Mars probes are. You still care about cleanliness for engineering reasons, but you're not worried that a few bacteria on a bolt will colonize lunar dust and evolve. So the moon becomes a testbed where you can focus on survival, construction, and operations without constantly wondering, are we killing something we haven't even discovered yet? Now compare that to Mars and icy moons. Mars has an atmosphere, thin but real. It has seasons, dust storms, polar caps, and subsurface ice. We've seen hints like seasonal methane plumes, small bursts of methane in the atmosphere that come and go with time. We've seen recurring slope linea, dark streaks that might be linked to briny flows, though that's still debated. It's not a lush world, but it has the ingredients that make scientists nervous: liquid water in some form, energy sources, and organic chemistry. Then go further out to moons like Europa and Enceladus. Under their ice crust, there are subsurface oceans, global layers of liquid water tens of kilometers deep, with evidence of hydrothermal activity on the seafloor. Those are serious candidates for alien habitats. So here's the problem. When you send a human to a place like that, you don't just bring a person, you bring their microbiome. Your skin, your gut, your gear, everything is coated with bacteria and other microbes. Even after cleaning, you're never sterile. Forward contamination is the term for what happens when you let those Earth microbes loose in a new environment. On Mars or an icy moon ocean, that could mean seeding a fragile native chemistry with hardy Earth life that might outcompete any local organisms, or confuse the science so badly that you can't tell what's native and what's imported. Ask yourself what happens if an astronaut leaks some waste, or a suit seal slowly releases air with microbes, or a lander crashes and spreads debris. On the moon, it's just trash. On Mars, those microbes might find the niche. In an icy moon ocean, one broken probe could dump contamination into an entire global sea that we can't clean up. Once you do that, you can't undo it. You've altered that world forever, and future missions may never get a clean read on what was there before we arrived. Then flip the direction. Backward contamination is the fear that something from out there might come back here. Right now, all of our sample returns are robotic and hyper-controlled, small pieces of rock or dust sealed in specialized containers. Even then, they go into strict lab environments with careful protocols because we can't be 100% sure what chemistry or biology might be hiding in them. Now, imagine returning not just a few grams of rock, but whole astronauts and large sample loads from a place that might have a biosphere, like Mars or the subsurface ocean of Europa. You suddenly have to ask ugly questions. What if there is some microbe that can survive in both environments? What if it's harmless? Or what if it isn't? We don't know. So you're forced to build extreme quarantine systems. Astronauts might have to stay in isolation for weeks or months. Samples might have to be handled in maximum security biolabs with multiple physical barriers between them and the outside world. Return capsules might have to be designed to be almost impossible to breach accidentally, surviving re-entry, landing, and any reasonable crash scenario without leaking. All of that is extra mass, extra cost, and extra complexity. Right now, we can barely manage strict cleanliness for robotic missions. Think about how hard it is to sterilize a small lander. You bake components, you assemble them in clean rooms, you track every process step, and you still can't get to perfect zero microbes. Scaling that up to a whole crude system is a nightmare. You can't bake an astronaut. You can't run a habitat through an oven. You have air, water, waste, food, and constant human activity. The best you can do is isolate certain parts of the system, keep the outside hardware as clean as possible, and control where and how the crew interacts with the environment. That operational overhead is a huge drag. Every EVA becomes not just go out and work, but make sure nothing we carry can shed biological material into sensitive zones. Sample handling has to be done through sealed tools and ports. Habitats may need airlocks that do more than just handle pressure. They might need chemical or radiation treatments for surfaces or complex filtration schemes for suit exhaust and leaks. You end up with a layered protection architecture, biological, chemical, and mechanical, wrapped around every human interaction with the planet or moon. From a mission design perspective, that's another heavy load. You have to design suits, landers, rovers, and labs that are not only safe and functional, but also meet planetary protection standards. You need extra structures to separate clean and dirty zones. You need monitoring systems to track contamination, and you need protocols for what happens if those lines are crossed. It's no longer just keep the crew alive, it's keep the crew alive without destroying the science and without risking Earth when they come back. Now look again at the moon. It has no known biosphere, no ozone layer, no surface water cycles, and its potential underground ice is locked away in conditions where life, as we know it, would struggle. From a planetary protection standpoint, it's low risk both ways. We're not likely to wipe out a hidden lunar ecosystem, and the odds of the moon harboring a dangerous pathogen that could survive and spread on Earth are incredibly low. That makes it the perfect sandbox, a place to push human exploration and build infrastructure without triggering the hardest planetary protection rules. So what quietly happens is this. The moon becomes the natural ceiling for human presence under current policies and ethics. We can send people there, learn how to live off Earth, test habitats, build bases, and even practice resource extraction, all while staying inside a comfort zone where contamination risk is minimal. But as soon as you talk about humans on Mars, Europa, Enceladus, or other potentially habitable worlds, the entire conversation shifts from can we build the rocket to are we willing to risk altering or infecting an alien environment and maybe exposing our own biosphere in return. And remember, all of these planetary protection systems, all of this quarantine and isolation gear has to work perfectly over multi-year missions on top of everything else we already stacked on the ship. You're asking hardware to be biologically clean, mechanically tough, and ultra-reliable in an environment that naturally breaks machines. Which leads directly into the next hard limit. Even if you accept all the ethical and scientific constraints, can you actually build a spacecraft whose pumps, seals, computers, and structures behave almost perfectly for years in deep space, when the only example we have of a long-lived crewed system, the ISS, survives only because it's constantly repaired and resupplied from just 400 kilometers away? You're asking machines to behave almost perfectly in an environment that chews up machines. And the only real example we have of a long-lived crewed system, the ISS, is actually a warning, not a template. On the International Space Station, things break all the time. Pumps fail, seals start leaking, valves stick, toilets clog, batteries age, power electronics burn out, solar arrays slowly lose performance. The reason the station is still there after more than 20 years is not because it's perfect hardware. It's because it lives only about 400 kilometers above Earth, roughly 250 miles, and it gets regular cargo ships full of spare parts, tools, and upgrades. On top of that, there's a whole army of engineers on the ground watching every sensor, writing new procedures and planning repairs in detail before the crew even touches a wrench. So when a key pump fails on the ISS, you can send up a replacement on the next cargo flight. If a whole piece of hardware turns out to have a design problem, you can redesign it on Earth, build a new version, and ship that too. It's messy, it's expensive, but it works because the station is still sitting in Earth's backyard. If you tried running the ISS with no resupply, no new parts, and no ground help beyond delayed advice, it would be a very different story. Now take that safety net away. A deep space habitat beyond the moon has to carry every critical spare part it might need for the whole mission. Years, not months. Think about something simple like a life support pump. Let's say its average time to failure is about 3 years. That doesn't mean it always lasts 3 years. It means statistically, some will fail earlier, some later. If your mission is 3 years long, you probably don't want just one pump and one backup. You want multiple independent pumps, maybe in parallel, plus spare units in storage in case one fails early, plus the tools and knowledge to remove and replace them in microgravity without making things worse. Now repeat that logic for air fans, CO2 scrubbers, water recycling units, valves, heaters, sensors, computers, power converters, batteries, and everything else that keeps you alive. The spare parts list explodes. You're not packing a weekend toolbox. You're packing something closer to a small factory storeroom. All of that is mass, and all of it has to be launched and integrated, and it all has to sit in storage for years before you even use it. Then there's radiation hitting your electronics. Outside Earth's magnetosphere, high-energy particles are much more common. They slam into chips and memory cells, flipping bits at random, something called single-event upsets. One flipped bit in the wrong place can crash a computer or corrupt data. Over time, radiation also physically damages semiconductor structures, slowly degrading performance. To cope with that, you need radiation-hardened components, which are usually bulkier, slower, and more expensive. You need more shielding around critical electronics, which means more mass. And you need redundant computing, multiple independent processors running cross-checks so that if one unit glitches, the others can vote it out. That's still not the whole story, because materials themselves age under space conditions. Polymers, the plastics and rubbers used in seals, cables, and insulation, can embrittle under UV light and radiation. They slowly crack, lose flexibility, or start to crumble. Lubricants and bearings and moving parts can outgas in vacuum, slowly evaporating away or migrating where they shouldn't be. Thermal cycles, going from hot to cold again and again, can cause microcracks in solders and joints. Solar panels degrade under constant particle and UV bombardment, so your power margin shrinks over time. For a 10-day lunar mission or even a 6-month ISS day, you can mostly ignore those slow drips. The materials don't have time to reach the failure point, and if they do, you probably have a replacement nearby or you're close enough to come home. For a 1,000-day mission, around 2.7 years, those slow degradations add up. A tiny leak in a seal that wouldn't matter for months might turn into a serious air loss over years. A small drop in solar array efficiency might turn into a power shortage that forces you to shut down non-essential systems, which then start to fail from lack of use or lack of heating. A bearing that's just beginning to run dry could see that exactly the wrong moment when you need to move a valve or rotate a radiator. The deeper you go into this, the more you see a cliff. Our current human space hardware is optimized for missions measured in months, maybe a few years, with the assumption that resupply and repair from Earth are always possible. We design things knowing they will be serviced, not sealed in a closed system for a decade. Demanding multi-year standalone reliability with no resupply pushes us into completely new design territory. You're talking about parts that have to be built, tested, and qualified to standards we rarely use because they would be overkill and too expensive for most near-Earth missions. And we don't have much operational data up there yet. We have long-lived satellites and probes, yes, but most of them are not human-rated. They don't have the same redundancy, they don't deal with cabin air, water, and waste, and they can be allowed to fail gracefully. If a 50-year-old probe stops working, it's sad, but no one dies. A deep space habitat doesn't get that option. You need the long life of a successful robotic mission combined with the safety and complexity of a crewed system. That combination hasn't really been built and proven in the field. All of this feeds back into the earlier problems. More redundancy, more spares, more hardening, and more robust materials all add mass and cost. The more you try to protect yourself from the harshness of deep space over years, the more your ship looks like a heavily armored, overbuilt industrial facility, not a sleek capsule. And as the ship gets heavier and more complicated, it becomes harder to launch, harder to assemble, harder to test on the ground in any realistic way, and harder to guarantee that no hidden flaw has slipped through. So you hit this reliability cliff just past the moon. Inside the Earth-Moon system, with fast return options and resupply, we can tolerate a certain rate of failure. We can let machines be imperfect, patch them, and keep going. Beyond that, you need a level of reliability and self-sufficiency that we've never actually demonstrated with people aboard. That's not a hard physical law like gravity, but in practice, it acts like one. It's another barrier that keeps human presence clustered near the lunar sphere. And even if you somehow solve that, even if you build a ship that can take the beating for years without falling apart, there's still a final twist from the physics side. You don't get to choose freely when to go or how quickly to come back. The planets are moving, the routes are fixed by orbital mechanics, and the launch windows that might let all of this work are rare, unforgiving, and very easy to miss. Even if you solved everything else, orbital mechanics still acts like a boss battle you can't cheat because the positions of Earth, the Moon, and the planets tell you when you're allowed to go, how long you're going to be stuck in transit, and how hard it is to come back if something goes wrong. Start with the easy case, the Moon. The moon orbits Earth roughly every 27 to 29 days. That means launch windows are frequent and forgiving. If a rocket has an issue on the pad or weather kills a launch, you don't lose the whole mission profile for years. You wait days to a few weeks, adjust the plan, and try again. The trajectories are relatively simple. You're essentially falling from Earth orbit to the moon's orbit around the sun. That short flight time keeps life support demands low and limits how much radiation, microgravity damage, and hardware wear you stack up just getting to the target. That frequent access matters more than it sounds. It means you can afford to fly practice missions, test new hardware, and even fail without the calendar destroying you. If one lander design doesn't quite work, you can iterate and return. The whole system becomes something you can refine step by step because each attempt is not a once-in-a-decade opportunity. In engineering terms, the moon lets you run many cycles of build, fly, fix, which is exactly how you make complicated systems safer. Now jump to Mars. If you want an efficient path, you use something like a Hohmann transfer, a low-energy orbit that connects Earth's orbit and Mars's orbit around the sun. Those transfer windows only line up roughly every 26 months. That means if your rocket has a serious issue near the window or a key system fails qualification just before launch, you don't delay by a week, you risk sliding the entire mission by more than 2 years. Every missed window is not just a schedule slip, it's a financial hit, and it can kill programs. And that's only the launch. Once you actually commit, transit times explode compared to the 3-day jump to the moon. A typical Hohmann transfer to Mars takes on the order of 8.5 months, one way. So your life support, your radiation shielding, your propulsion, your power systems, your navigation, all have to work well enough for almost a year just to get you to the starting line at Mars. Then you still have to capture into orbit or land, operate there, and eventually do another long return leg. Those months in transit are not dead time, they are risk exposure. Every extra day is another dose of radiation, another set of thermal cycles, another round of micrometeoroid exposure, another day for a pump to fail or a microcrack to grow. On a lunar run, if something starts to drift out of spec, you might be willing to ride it out because you know you're home in a few days. On a Mars transfer, if a trend appears in month 3, you've still got 5 or 6 months to go with that same hardware. You can't just wait it out. Your system has to be robust across that entire period. Navigation adds another layer. When you leave Earth for a deep space target, even tiny errors in your initial velocity and direction, fractions of a meter per second, small angle offsets, will grow over tens of millions of kilometers. The farther you travel, the more those little deviations compound. So mid-course corrections are not optional. They are built into the mission design. You schedule small burns to trim your path, adjust for small errors, and make sure you hit the arrival corridor correctly, whether that's a narrow slice of atmosphere for aero capture or a precise orbit insertion point. Those correction burns depend on your propulsion system being healthy and responsive at exactly the right times. If an engine is degraded, a valve sticks, or a tank's pressure is off when you need a burn, you may not be able to correct enough. That can mean arriving at the wrong altitude, hitting the atmosphere too steeply, skipping out into a bad orbit, or missing the planet entirely. When people say navigation, they're not talking about just knowing where you are. They're talking about having the capability to change where you're going in a controlled way after months of drift with very little fuel margin. Now think about aborts and windows together. For the moon, short transit and frequent windows mean you can mess up, learn, and try again without waiting half a decade. You can build an architecture around that, test landers, test habitats, test refueling, and if something goes badly wrong, your next opportunity is just around the corner. The environment punishes you, but it also lets you iterate. Deep space missions are the opposite. The windows are sparse, the trajectories are long, and the arrival boxes are tight. You only get a few shots per decade to try a major architecture. If you discover a design flaw halfway to Mars, you can't adjust on the next flight a few months later because there is no next flight for years, and you may not even have a functioning program by then. That makes everyone more conservative. Human-rated systems are already designed with a lot of margin, but when the mission is rare and unabortable, the required level of confidence rises again. This is a brutal standard for hardware and for planning. The risk per attempt is high, the number of attempts you can afford is low, and the time between attempts is long. If you compare that to air travel or even to low Earth orbit operations, it's the opposite of how we normally make systems safe. Airliners fly thousands of times, flaws show up in service, and fleets are upgraded. Even rockets going to orbit get flown, refined, and reused. For a Mars-class crewed mission, you might realistically only fly the full system a handful of times across many years, and early failures could end the whole effort. So, orbital mechanics quietly pushes humans back toward the Earth-Moon neighborhood. Short, frequent windows to the moon, trajectories you can reattempt often, and 3-day transits create a forgiving environment for learning. You can gradually expand capabilities, stretch mission durations, and upgrade hardware while still having frequent chances to practice. Once you try to move beyond that, the physics of transfer orbits forces you into missions that must be nearly perfect on very rare chances. That's not a great match with fragile human bodies, complex life support, and systems that don't like visible failures. And on top of that, all of these constraints don't only hit your engines and your launch schedule, they land squarely on the people on board. You're asking a small crew to commit to years in a metal tube on a path they can't change much, with almost no real-time help, knowing that if something serious breaks or someone gets badly sick, there is no fast way out. That's not just an engineering challenge, it's a psychological and social pressure cooker, and there's a limit to how far you can push human minds under those conditions before that becomes its own hard boundary. You're not just shipping bodies into space, you're shipping minds into isolation, and that quietly becomes one of the hardest limits once you go beyond the moon. Right now, the best human test chamber we have is the International Space Station. Crews live there for 6 to 12 months at a time, in a volume about the size of a big house if you add all the modules together. They can float from room to room, look out the window and see Earth sweeping by every 90 minutes, watch cities at night, storms, auroras. They have regular live video calls, emails, voice chats, constant contact with mission control, and fast return capsules docked right there. Even with all of that, psychological stress is real. People get irritable, they miss home, they feel trapped. They have to manage conflicts in a small, noisy, cluttered environment. Now, strip almost all of that away and ask what deep space feels like. On a Mars or outer planet trajectory, there is no giant blue Earth hanging outside the window, no familiar continents, no sunrise every 90 minutes. Most of the time, if you look out, you see black, a few stars, maybe a faint sun that gets smaller the farther you go. You know very clearly that you're tens of millions, maybe hundreds of millions of kilometers from home. You know that if something bad happens, there is no quick evacuation, no emergency capsule that can drop you into an atmosphere in a few hours. That awareness changes the way stress lands. On the ISS, no matter how rough your day is, there's a part of your mind that knows if absolutely everything goes wrong, there is at least a path to jump in a capsule and be on the ground the same day. Beyond the moon, that safety story is gone. There is no same day. There is months from now if the ship and the trajectory cooperate. You're not just far, you're committed, and that commitment sits in your head every single day. Then add communication lag to that. With 4 to 24-minute one-way delays, you can't pick up a headset and casually talk to your family. You can't have a real-time therapy session where someone listens and responds in the moment. You can't even have a normal conversation with mission control. Everything becomes a delayed exchange, closer to trading voice emails than talking. You send a message, you wait, they respond, they wait. By the time the reply reaches you, your mood might already have shifted. The situation on the ship might have changed, and the emotional impact is different. That lag quietly cuts the strength of your social ties. On the ISS, you can see your kids live on a screen. You can react to what they say. You can joke and share things in real time. In deep space, that becomes record a message, receive a message, with a built-in gap that you can't remove. It's a slow drip of distance that we haven't really experienced yet, not for years at a time, with the added pressure of knowing you can't physically come back until the trajectory allows it. Now look inside the ship. You're living with a small group of people, maybe 4, 6, something like that, in a confined volume. Even if you design a larger habitat, it's still small compared to any building on Earth. There are no days off where you go to a park, no stepping outside alone, no fresh air, no real change in scenery. You see the same faces, hear the same voices, and deal with the same habits every day for hundreds of days. No one can leave, no one new comes in. There is no rotation of crew like on the ISS. Small group dynamics under those conditions are not a side issue, they're core mission risk. Minor annoyances can grow into big resentments if they're not dealt with. Differences in work style, culture, or stress response can turn into real conflict. And there's nowhere to go. You can't walk around the block to cool off. You can't get true privacy beyond maybe a small sleeping compartment with a thin wall. If two people really can't stand each other, you can't separate them into different teams on different shifts and different modules very easily, because the ship itself is limited in size, and every task requires coordination. We know from submarines, polar stations, and analog studies in isolated habitats that even well-selected, well-trained people feel the strain over long periods. Mood disorders, sleep problems, tension, and breakdowns in communication can appear. Now, picture that in a place where, on top of everything, you're in zero G, dealing with physical discomfort, constant noise from fans and pumps, and the underlying knowledge that a serious mistake might kill everyone, not just you. The psychological load is heavy, and it doesn't let up. You can try to mitigate this with careful crew selection, lots of training in conflict resolution, strong routines, entertainment options, virtual reality, recorded messages from home, structured schedules, shared goals. You design the interior to give as much personal space as you can. You build in quiet time. You watch mood indicators and performance closely. But none of that changes the basic fact that you're running a multi-year, high-stakes social experiment in a sealed can, with no way to replace a crew member who burns out or becomes unstable. From a mission design standpoint, that introduces another kind of risk you have to plan for. You need protocols for what happens if someone becomes clinically depressed or paranoid or starts making unsafe decisions. You need ways for crew members to report psychological problems without fearing punishment or stigma. You need onboard tools, maybe digital therapy support, maybe training in self-management, because ground-based psychologists can't interact in real time. And you need to accept that even with all that, some missions might fail not because a pump broke, but because a crew's internal dynamics did. Now think about how the moon fits into this. A lunar mission, even a longer one, lets humans experience distance and isolation, but with quick return and real-time support still in the picture. You can send crews for weeks or months to a base on the surface, test how they deal with confinement, darkness, and routine, and if someone starts to show severe issues, you can realistically plan an early return within days. Psychologists on the ground can talk to them live, watch them over video, and adjust support as needed. You get data on what works and what doesn't without trapping people years away from help. Beyond the moon, that psychological safety net breaks in the same way the engineering one does. You commit people to a timeline that can't be shortened, which is a huge mental weight. You reduce the support bandwidth and increase the delay. You remove the visual anchor of Earth in the window. You make every relationship on board more loaded because everyone knows they are stuck with each other until the trajectory says otherwise. That is not a small adjustment. It's a different regime of human experience. So when you stack everything up, physics and engineering are not the only barriers. Human minds have limits too. We don't fully know where those limits are yet, but we know they exist, and we know that pushing past the moon means pushing into psychological territory that isn't mapped. That alone makes decision makers cautious, because you're no longer just betting on metal and fuel, you're betting on how a handful of people will behave under pressure for years, with no escape. And even if you could guarantee perfect crews, even if you had astronauts who were somehow immune to isolation and stress, you still run into one last filter: the layer of policy on Earth that decides which missions happen at all. Physics might allow something, engineering might barely handle it, but if leaders and voters are not willing to accept the cost and the risk, then in practice, it stays impossible. Physics doesn't decide alone. Voters decide which missions actually fly, and that's a big part of why you're still stuck near the moon. Look back at Apollo. That program didn't happen in a vacuum. It rode on Cold War urgency. The United States and the Soviet Union were locked in a competition for prestige and influence, and the moon became a scoreboard. That pressure justified risk levels that would look insane today. Apollo 8 took astronauts around the moon in December 1968 in hardware that, by modern human rating standards, was not fully proven. The Saturn V had just had a major problem on Apollo 6. The command and service module design was still evolving. But the drive, beat the Soviets, show capability, pushed the risk calculus. We'll go even if the safety margin is thin. And that decision came right after Apollo 1, where a fire in a ground test killed 3 astronauts inside their capsule. That alone could have shut the whole project down. Instead, they redesigned, improved, and kept going because the motivation was still there. Risk was accepted because the goal was seen as vital to national pride and strategic signaling. That kind of environment lets missions through that would never clear today's filters. Now, fast forward to post-Apollo and the shuttle era. After Apollo ended, the big, urgent race was over. The narrative shifted. We got the space shuttle, pitched as a reusable space truck to make spaceflight more routine. Then, Challenger in 1986 and Columbia in 2003, both lost with their crews. Both failures replayed in slow motion on television and then online. Each disaster triggered investigations, public anger, and a deep rethink of acceptable risk. Human spaceflight got reframed around low Earth orbit with tighter safety expectations, heavier checks, and more layers of review. That caution has only grown. When you put humans on a rocket now, you don't just answer to engineers and generals. You answer to the public, to families, to media that can broadcast every detail worldwide in seconds. Losing a crew on the way to the ISS is bad enough. Losing a crew halfway to Mars with no hope of rescue, with months of slow deterioration broadcast and analyzed in real time, would shape public opinion for decades. Leaders know that. Agency heads know that. It sits quietly behind every decision. Deep space accidents wouldn't be quick. If a major failure happens halfway to Mars, the crew might survive for days or weeks as systems slowly degrade. The world would watch. Commentators would speculate. The images and audio would live online forever. That kind of potential outcome makes governments extremely conservative, even if the underlying physics says this mission is technically possible. So you get a kind of psychological safe zone, and right now that safe zone ends at the moon. The moon is far enough to feel like true exploration. You're not just circling Earth, you're landing on another world. But it's close enough that a rescue or retrieval feels at least imaginable. If something goes wrong in lunar orbit, you can talk about rescue plans in days, not years. If a lander fails, you can sometimes recover hardware later. You can bring bodies home. You can give families and the public some sense of closure. That matters more than most technical discussions admit. Systems like missions where if the worst happens, they can still say we tried everything and point to realistic emergency options. The moon gives you that. You can design free return paths. You can carry extra fuel for fast returns. You can keep abort options on the table almost all the way. Even if you never use them, the fact that they exist makes it easier for leaders to sign off. Mars or beyond doesn't give you that comfort. Once you're on a long transfer out, the concept of rescue is basically gone. Another ship can't catch you. A return burn that gets you home faster may not be possible. If a crew dies out there, there may be no practical way to recover their bodies. The story becomes we launched them, they disappeared into deep space, and they never came back. That's hard to sell in any system, especially when people on the ground are asking why that money wasn't spent on problems at home. The moon, again, fits better into this reality. You can break a lunar program into smaller steps, each with visible progress, each close to home. Orbital tests, uncrewed landings, short crewed trips, longer stays, small bases. If one mission fails, the next is only months away, and you can adjust. International partners can join, companies can contribute, the whole thing looks like a shared project, not a single massive bet. So when you hear people say it's impossible to go beyond the moon, what they often mean, without saying it directly, is it's impossible to get enough will and public acceptance to fund and fly missions that dangerous for that long. On paper, engineers can draft a Mars transfer vehicle, calculate fuel loads, design life support, and draw trajectories. Physics doesn't forbid it, but on paper doesn't sign budgets or face voters or speak at memorials if things go wrong. In practice, the real threshold of what societies are willing to risk and pay for right now sits roughly at the lunar boundary. Beyond that, the combination of cost, time, and potential for very public catastrophe pushes decision makers into not yet mode. They wait for cheaper launch, better propulsion, better life support, more robotic data, and maybe a different level of public appetite for risk. That's why today the moon acts like a practical wall. Not just gravity, not just radiation, not just engineering, but psychology all stack up at about 384,000 kilometers. You live inside that bubble. Everything beyond it is still mostly concept art and slides. So the real question becomes, what would have to change across all of this for that wall to crack? What kind of propulsion? What kind of shielding? What kind of life support? What kind of ships? And what kind of cultural shift would finally make going beyond the moon feel not like suicide with extra steps, but like a hard, expensive, dangerous mission that we can actually justify and survive? If going beyond the moon feels impossible today, what would actually have to change before you could look at Mars or anything further and say, yeah, that's hard, but it's doable, instead of that's suicide with extra steps? First, you need engines that stop punishing you for wanting to go far. High-efficiency propulsion is the foundation. Right now, your chemical engines throw exhaust out the back at a few kilometers per second, around 4.4 kilometers per second for the best hydrogen-oxygen engines, and that locks you into that brutal fuel spiral. Nuclear thermal propulsion changes that game by using a reactor to heat hydrogen and throw it out much faster. Double the exhaust speed, and suddenly for the same change in velocity, you don't need nearly as much propellant. That means you can spend more of your mass on what you actually care about: thick radiation shielding, big life support systems, redundancy, and structure that's not paper thin. Go further, and you get into advanced electric propulsion fed by nuclear power. Very high-efficiency thrusters, exhaust speeds in tens of kilometers per second, powered by a compact, constant energy source instead of gigantic solar arrays. That lets a heavy ship slowly but steadily build up speed, cut down trip times compared to chemical only, and still carry the armor and redundancy you need. But right now, these systems are mostly on paper or in small-scale tests. Nobody has flown a human-rated nuclear rocket. Nobody has run a megawatt-class electric drive with a crew aboard in deep space. Until you do that, chemical rockets keep you mostly pinned near the moon. But say you solve that. Say you have engines that can push a serious deep space habitat. Then you hit the next wall: radiation. Serious radiation shielding has to move from thin aluminum shell to this ship has a built-in bunker. You'd be looking at smart use of hydrogen-rich materials, because hydrogen is good at slowing down charged particles. Water walls around crew quarters, tanks of hydrogenated plastics, fuel and water arranged as a shield instead of just dead mass. You might store water and propellant in a torus around the living volume, so every kilogram you need anyway is also part of your armor. And behind that, you probably need some form of active shielding. That could be magnetic fields or electric fields that try to bend or repel incoming charged particles. Basically, a miniature artificial magnetosphere around the ship. In theory, that could cut the deep space dose from hundreds or more than 1,000 millisieverts per mission down to something closer to what ISS crews see, tens of millisieverts over months. But to do that in practice, you need powerful fields, superconducting coils, big power systems, and extremely stable control. If it glitches, you don't just lose a subsystem, you expose the crew to a radiation spike. So you're stacking another complex, high-energy system on top of everything else. Even if you knock radiation down to a tolerable level, you still have the problem of supplies. Closed-loop life support that really works is non-negotiable beyond the moon. You're aiming for near total recycling of water, oxygen, and maybe a big chunk of your food chain. Instead of tens of tons of consumables per person, you want to bring only a few tons and keep cycling them. That means better water recovery than the ISS, better air revitalization, and probably some mix of biological and mechanical systems. Algae or plants to scrub CO2 and produce oxygen, plus machines to back them up when they misbehave. On top of that, you need onboard manufacturing of spares because you can't pack a replacement for every single component. That might look like robust 3D printers that can work with metal and polymers, recycling broken parts into raw material, plus standardized designs so you can rebuild a valve body, a bracket, or a housing on the fly. You'd still carry critical items you can't print, like certain electronics, but everything else has to be part of a circular system. And you don't just have to build it, you have to prove it. Multi-year tests, maybe on the ISS or on the moon, where you run the loop without cheating. No secret resupply, no hidden water tank feeding the system when the numbers get ugly. But even if the chemistry and recycling is perfect, your body doesn't care. It still wants gravity. That's where artificial gravity habitats come in. To stop your bones from dissolving and your muscles from wasting away, you need some sustained load. Rotating sections that provide between 0.3 and 1 g would give you that. Spin a ring or a long tethered system so that the outward force feels like weight. Now your skeleton has a reason to stay strong. Your heart has to pump against a gradient again, and the worst fluid shift problems might ease off. The problem is these structures are big and heavy. To make the spin comfortable so you don't get motion sick, you want a large radius, not a tiny hamster wheel. That means tens of meters of structure, maybe hundreds of meters if you're ambitious. The rotation creates stresses in the frame. Bearings or joints have to survive for years. Docking becomes more complicated, and you have to manage gyroscopic effects when you try to turn the ship. Nobody has ever flown a large spinning habitat for people, even in low Earth orbit. You'd be jumping straight to using it in deep space, where any structural failure is catastrophic. So picture what you've built so far in your head. A ship with high-efficiency propulsion, a thick and maybe active radiation shield, a closed-loop life support system with onboard manufacturing, and a rotating section providing artificial gravity. That's already a huge, expensive, complex machine. You still have to design it so that if parts of it fail, you don't instantly lose the crew. You still need redundancy, repair capability, navigation, communication, all the things from the earlier sections. And then you run into the last filter, which has nothing to do with what engineers can draw and everything to do with what society is willing to sign off on. You need a new risk contract with humanity. Right now, people subconsciously expect human spaceflight to drift toward commercial aviation levels of safety. Very low risk, many flights, failures so rare they become global shocks. Deep space exploration is not going to look like that, not for a long time. It will look closer to early polar expeditions or the first long ocean voyages, missions where everyone involved knew there was a real chance of death, where ships were lost, where crews disappeared. If you want humans to go beyond the moon, you have to accept that some missions will fail, and not quietly, but in front of the whole world. That means being honest, upfront, that deep space flights will be expensive, slow to prepare, and genuinely dangerous. It means building multinational, multi-decade programs that don't instantly collapse after one bad incident. It means training crews not just as pilots and scientists, but as mechanics, medics, and leaders who know that help is not coming. And it means voters agreeing that the benefits, scientific and symbolic, are worth the risk of watching a ship vanish into the dark and never return. If you start stacking all of this together, you can see the path. High-efficiency engines that can push heavy, safe habitats, real radiation protection that makes multi-year trips survivable, closed-loop life support that doesn't need constant rescue from Earth, artificial gravity to keep bodies functioning, and a culture that understands this won't be clean, cheap, or safe for a long time. Only when those pieces lock together does the impossible line move beyond the moon. Until then, the moon stays as the hard edge of your world, the place where everything you have today just barely holds together. Beyond it, the physics, the engineering, the biology, and the money all line up on the same side, and they all say the same thing: not yet. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.